Hey, Marissa, what are you doing?
I wish I could do that.
I know, they're amazing. I wonder how they even do that.
Let's Google it.
What are you Googling?
I want to know how she did that. So how do people, not how do people survive Ebola, how do people turn fancily in dance? What does that mean?
That's a big word, but I think angular momentum is the quantity of rotation of a body, which is the product of its moment of inertia and angular velocity. Angular momentum is also known as rotational momentum. By taking into account the object's speed, mass, and shape, the angular momentum describes the amount of rotation an object has.
Wow, that's really cool, Lexi.
Thanks, but you know what I don't know is what angular velocity is.
I think I could help you on that one.
All right.
Angular velocity, also called rotational velocity, is a quantitative expression of the amount of rotation that a spinning object undergoes per unit time. It's a vector quantity, so that means it has an angular speed component and a direction. Angular velocity is how fast an object can turn in a designated direction. The angular speed of an object is directionally proportional to the length of the angular velocity vector. Angular velocity and speed are directly correlated. Now, what I don't know is what moment of inertia is.
Oh, I got this. A moment of inertia is a mass property that determines the force needed for an angle to rotate around an axis. A moment of inertia depends on the shape of the body and may be different around different axes.
I want to know more about this. Do you think when a dancer moves, she's doing work?
Well, luckily I've taken a few dance classes in my life and I know some physics behind it. And a dancer does do work. Every time a dancer moves, she's doing work. To do work, the dancer needs energy.
Well, where does the energy come from?
The energy comes from the food she eats, which has chemical potential energy, which is then transformed into kinetic energy.
Is any other energy present?
Yeah, also gravitational potential energy is present every time the dancer is lifted or does a jump or a leap. Dancers keep their balance by holding their center and by keeping their body in line with their center of gravity.
How does a dancer do all those turns and not get dizzy?
Dancers use something called a spot that makes them not get dizzy. A spot is when you whip your head around and look at one thing. The turning motion of the dancer's head also assists the dancers on maintaining balance and it helps them gain momentum.
So how is a turn produced?
Well, a torque is a very important part of the ability to turn.
Twerk? Did you just say, oh my gosh.
No, torque. T-O-R-Q-U-E. A torque is the tendency of a force to rotate an object around an axis. A torque is a measure of the turning force an object that can rotate.
Okay, but then how is that possible?
A turn is possible by the friction that is produced by pushing off the floor. In a fouette turn, my favorite turn, the extension and retraction of the leg affects the rotational inertia. When the leg is open, one speed is slower, and when the leg is closer to the center of gravity, one speed is faster. A dancer is able to change the speed of the turn by extending and retracting her leg because of the angular momentum. When a dancer pushes off the floor and the initial torque has been applied, the angular momentum will stay constant. It will only decrease from an outside force of friction from the floor. The dancer's angular momentum depends on the moment of inertia and the velocity of the dancer because the moment of inertia and velocity are in the equation. If the dancer did not change speed, he or she would be violating the law of angular momentum conservation. Do you know what that is?
You see, just like mass and inertia, angular momentum is a conserved quantity. The law of conservation of momentum states that the total angular momentum of a system has constant magnitude and direction if the system is subjected to no external force. Just like other conservation laws in physics, the law of conservation of angular momentum states that the amount of momentum cannot be created or destroyed, but it can be transferred. So this is how we'll calculate your angular momentum. The formula for this is angular momentum equals the moment of inertia multiplied by the angular velocity.
Oh, okay, but don't we need to figure out my moment of inertia before we figure out my angular momentum?
You're right. The formula for the moment of inertia is mass multiplied by the radius squared.
Oh, okay, well my mass is 50 kilograms and the radius of my leg is 1 meter. So do we do 50 times 1 squared equals 50?
Mm-hmm.
Oh, okay.
Now we'll plug 50 back into the angular momentum formula.
Okay, problem. What is my angular velocity?
Your angular velocity is how many times you turn per second.
Oh, so 2.
So what we would do is multiply 50 by 2, so we get the 100 kilograms meters squared per second. Now notice Lexi's speed when her leg is pulled out.
Ah, I get it, but how does this help me figure out my angular momentum when my leg is pulled in?
Well, according to the law of conservation of angular momentum, you cannot lose it, so you'll always have 100 kilograms meters squared.
Okay.
So let me show you what we're going to do. So you have the 100, and that comes from the previous equation, which is the moment of inertia multiplied by the angular velocity. But we have to figure out the moment of inertia first. So your mass is going to stay the same as before.
Are you sure? I kind of had a big breakfast. I don't know if that's going to affect it.
I don't think that will change much. So your mass stays the same, but your radius is going to decrease to 0.25. So again, once we solve, we'll get 50 times the 0.25 squared and divide that by 100 to find the angular velocity, which comes out to be 32 meters per second. Now notice the increase in her speed when her leg is pulled in.
Well, that law makes sense because when my leg is out, I turn slower, and when my leg is pulled in, I go faster.
Well, now that I learned all of this information about the physics behind dancing, I think I could try.
Oh my gosh, yeah. 5, 6, 7, 8. Yay! Hey, so I have a question. Is linear momentum the same as angular momentum or not?
Not exactly. Angular momentum is the rotational counterpart of linear momentum. Linear momentum will always happen in a line, and it is the product of the mass and velocity of an object. And like I said before, angular momentum has to deal with the rotation of objects, taking into account their mass, shape, and their speed. So do any other athletes or people use angular momentum?
Oh my gosh, yeah. Figure skaters provide a perfect example of an incident where angular momentum is conserved. This is seen when a figure skater is turning. Only a very small quantity of friction exists between the skater's ice skate blade and the actual ice during the turn. Therefore, the figure skater is primarily seen as a closed system and her angular momentum is conserved. When a figure skater pulls in their arms closer to the center of their gravity, they are increasing their speed while decreasing their radius, just like a dancer. When the figure skater pulls their arms in tighter, the times per turn is less than it would be if their arms were outstretched.
You know, Lexi, I'm really glad I learned that angular momentum affects every rotating object, from a rolling tire to an ice skater to a ballerina, doing a double turn on her pointe shoes, to just everything that rotates. It really opened my eyes.
I know, same. I never realized how much the laws of physics and forces affect us and make a difference in our lives every day. Especially when I'm doing my favorite thing, which is dance.
Probably shouldn't be my favorite thing. I'm not too good at
You're
it.
improving. Let's go have a dance party. Come on.